Okay, so thank you for that introduction. It's a real pleasure to be here and be able to give you an update on our GCEP project on solid oxide flow batteries for grid energy storage. A couple years back, we gave a talk as well on the cell material advancements we've been working on. Today's talk, we're going to focus more on the system concepts that will hopefully enable the technology to move it forward. Before moving into that, I just want to acknowledge our team members, PhD student Chris Wendell and Professor Bob Key at the School of Mines, Professor Scott Barnett and Doctors Gareth Hughes and Zhan Gao at Northwestern, who are really working at advancing the cell technology. So in today's talk, I'm going to briefly give you an overview of what exactly is this technology, and followed by with, I guess I would say, our view of some of the motivation and the technology requirements that are needed for energy storage to move forward. I'll then move into some descriptions of reversible solid oxide cells as flow batteries. Here we'll look at a little bit at the theory of operation and performance considerations, as well as some performance estimates of really these large-scale, megawatt-size, gigawatt-hour capacity systems that we would envision for bulk storage. I'll give a brief update of some of the exciting developments in the cell development area where we're really trying to push towards a 600C operation cell using LSGM technology. We have some very interesting and encouraging results related to cycling to show of these cells, and that's very important when we're going to operate forward and backward modes with this technology. We don't want degradation there. Lastly, we'll touch on some of the economic projections for these kind of large-scale bulk energy storage systems. I'll then briefly touch a little bit on what we've learned in future directions. So in principle, a solid oxide flow battery really leverages similarities to fuel cells where we're going to operate reversibly. Here, reversibly is not in the thermodynamic sense. It's in the sense of reversing the current for these systems to operate in a power-producing mode and in electrolysis or charging mode. And we're going to tank the reactants and capture those in gaseous storage. And that's particularly useful for us because it gives us really the flow battery advantage. We get to decouple power capacity from storage. And so the power will scale with the size of the cell stack, and the energies will scale with the size of the storage tanks. We also get the high efficiency advantage of solid oxide cell technology, which enables us to have really high round-trip efficiencies as we move between modes. We don't experience high polarization in electrolysis mode, and the relatively novel HCO chemistry that is experienced directly within the cell allows us to produce high energy dense fuels. So shown here is a real simple schematic of a solid oxide cell, an oxygen conducting one with some fuel storage. Here we're showing methane and syngas. And we're going to feed it with air, and we're going to take the oxygen from air, reduce it, get those anions moving, and electrochemically oxidize those gaseous reactants into H2O and CO2. We will capture that tail gas in a tank and essentially produce our power. Now, in reverse mode, we can then accept, apply voltage, drive a current, essentially put our power into the device, and then move into the opposite mode where we'll remove those previous products of reaction out of storage, back to our cell. We'll strip out the oxygen, liberate some of that oxygen, and in the meantime, directly within the cell, we will produce methane and syngas. In general, that will give us favorable scaling this device, but also something additionally unique is it gives us really low-cost working fluids compared to advanced and other types of flow batteries. In terms of motivation, certainly the variability of renewable energy resources is well known and motivates developing grid energy solutions. I like to at least see some picture of what that means. Here are some minute-by-minute data shown from Hawaiian Electric Power on a wind farm. We can see really a 10x change within 30 minutes of the power requirements. And it's not just wind variability. If we look at developing activities and concentrating solar power and, of course, PV penetration, you've got power fall off in the evening hours as well that will need to be addressed to get high capacity factors. So currently, there is no battery technology that really serves. Most of our energy storage worldwide is predominantly pumped hydro. But this problem still exists, and those who are facing this, primarily often island nations, for example, are already trying to develop solutions, and I will call them poor solutions, taking high-grade electrical energy and storing it in low-grade hot water, for example, a so-called thermal battery. That's being done by Hawaiian Electric Power to manage this variability. It's also being done in electricity arbitrage models in Minnesota, for example. I would call them the dubious honor of having the largest thermal battery perhaps in the country at 1 gigawatt hours, high-grade electrical energy, low-grade hot water. It's essentially thermodynamic sin. But on the other hand, good economics doesn't necessarily always mean good thermodynamics. In general, though, in order to enable that technology, we've got to reach some certain targets. We've been keeping our eye on these as we look at this technology, certainly capital costs and round-trip efficiency, but perhaps most importantly, some levelized cost of electricity storage around a dime per kilowatt-hour cycle. We need cycle capability, and depending on the application, you'll need various modes, various duration of storage. If we now turn to looking at the technology itself, just operationally, we can take a look at a voltage current plot, which is a representation of the cell's performance characteristic. And shown here, we can see that in power producing mode or fuel cell mode, the voltage will decrease as you increase the current density or produce more power in response to overpotentials and irreversibilities within the cell. The slope of this curve represents the overall resistance. In fuel cell mode, the higher the voltage, the higher the efficiency. In electrolysis mode, we can see a relatively smooth transition shown here in this cartoon, but that's actually what we see experimentally as well. There isn't a large overpotential that gives us good electrolysis efficiencies, low applied voltage needed there. But here you want low voltage equals high efficiency in electrolysis mode. So if we look at the round-trip stack efficiency, which is not shown here, okay, is basically the voltage of the fuel cell divided by the voltage of the electrolysis device. That's the ratio. So you want high fuel cell voltage, low electrolysis voltage. That will give you a high round-trip efficiency. At the system level, we not only need to be mindful of the stack, but we're moving these reactants back and forth between the tank and the stack, and so there's an auxiliary power component that enters into this ratio. So in the end, how we can improve system efficiency, we can improve the cell by reducing overpotential, and at the system level, we got to be mindful of the balance of plant and thermal management. And when we look at thermal management, one of the unique attributes here is by doing methanation locally within the cell in an electrolysis mode, we're able to attain low electrolysis voltages, get towards a thermal neutral operation as well. So when we look at a fuel cell, it requires heat rejection. We're air cooled. We're operating at relatively high temperatures. But in electrolysis, this is, of course, an endothermic process. It requires a heat source. And we can see that when we reduce H2O, that's certainly the case. We're going to leverage HCO chemistry here, and because of the nickel in the fuel electrode, we can also do heterogeneous chemical reactions and reduce CO2 as well through H2 and provide us with some CO, which can then be combined with hydrogen to methanate, which is highly exothermic. Okay? And that's very nice for us because we have an exothermic local source where we have an endothermic process. We've got good matching of sources and sinks there. And ultimately, low temperature is what we would want and relatively high pressure to achieve that methanation. One of the considerations we're faced with as well is if we're going to design one of these systems, what do we charge the tanks with? What is the composition we want? And what are the considerations therein? So in these systems, we have to be concerned about carbon deposition. This is a deleterious effect on solid oxide cells. and it degrades their performance rapidly should that happen. So shown here is, in the right, is essentially a compositional space used in a so-called Gibbs diagram or ternary diagram, where the shaded area above the red indicates the thermodynamically favorable region for carbon deposition to occur. And the white zone really is unfavorable for that, and that's where we want to operate. So in doing so, you can see the red dot up here is where we might start on a hydrogen-carbon ratio, oxygen ratio for fuel cell mode. As we oxidize the fuel, we'll move towards this fully oxidized region shown in the light blue. And we don't really want to be fully oxidized. In this system, we want to be not fully oxidized and not fully reduced. This is our operating window, if you will, to move back and forth. If we look at the bottom graph, we can see basically on the left-hand side equilibrium gas constitution on a molar basis. It's a wet basis shown here versus oxygen content. And we can basically move back and forth shown here, between 4 and 40% oxygen conversion, which will allow us to have fairly high storage capacity. We can produce methane in a 60-40 ratio with hydrogen here on a dry basis. And at this end of the cell, so basically as you produce in fuel cell mode, you'll see us reducing the CH4, producing H2O. These, of course, will be tanked for electrolysis mode. So one of the proposed applications we've been looking at is really bulk storage. In order to get there, we need very large tanks. And very large tanks can be realized with pressurized underground gaseous storage of our reactants using salt caverns, for example, natural gas reservoirs, saline aquifers. And so this concept is actually being very seriously considered, particularly in Europe, in Germany. And we're looking in collaboration with the Danish Technical University at designing the so-called surface system, which will convert and store our reactants. Using survey data on natural gas reservoirs in Denmark, for example, we can estimate 500 gigawatt hours of storage would be available for one plant that has a 250 megawatt capacity. And the punchline here is, we'll get to this later, but in the end, these storage costs can reach 3 to 4 cents per kilowatt hour with storage durations of months. Which is particularly important. Germany in particular is very interested in month-long duration storage because of the low PV insulation and during the winter in particular. Because we produce methane, we find it really interesting that the technology is also suitable to support the so-called power-to-gas platforms that are very of increasing interest, particularly by Europe, in getting off of Russian natural gas and using renewable green electricity, if you will, to make SNG. This technology is perfectly applicable to that. In the end, though, we need this top surface system, and that involves systems integration and thermal management strategies in moving essentially between the caverns and the stack. And so just very briefly, we have to pressurize and preheat the reactants to get over to the stack. We can recover some of that energy from fuel cell exothermic operation to reduce our balance of plant parasitics. From the cavern, we'll take our CH4 preheated and expand it because it's operating at, say, 160 bar and the stack is at 20 bar. We'll recuperate some power and we'll introduce steam and use the tail gas, if you will, of that process to meet process heating needs before dumping it into the CO2 cavern. We'll get DC power out, and when we go to electrolysis mode, we basically reverse and store in the CO2 cavern, store in the CH4 caverns. Importantly, in order to make this viable, we want to use the same equipment. Okay, so that means they have to be sized and operated and designed such that that can be done. We also have to carefully manage water in these systems. We're going to knock it out and generate it because we can't really easily store it in these caverns and extract it. When we look at performance trades, clearly a key issue is what pressure and temperature should this stack be operated out. One of the things we like about this project is we got cell material development, we got systems aspects going on, and the two get to talk to each other, we can say from a systems view, I don't really need very low temperature, or I need a different pressure for you guys to focus on, perhaps, depending on the application. So here we show a plot of round-trip efficiency for the stack and the system. We'll just focus on that versus stack pressure. And we see an optima is here, and that optima basically is the interplay between the auxiliary power depending on what the stack pressure is. So if the stack pressure is relatively low, we can get net power out of our system in fuel cell mode, and that can offset our electrolysis pumping requirements. In the end, that interplay gives us an optimum of around 20 bar, which we like because that matches a lot of the high-pressure turbine spools that are available that might be integrated with the system. Similar trades are present when we look at temperature and reactant utilization, and those optima are shown here. If we just quickly move into now looking at some of the cell technology advancements that have been ongoing with this project, we're really focused on these next generation material sets, leveraging really LSGM technology to push towards 600C and with high cycle durability. Briefly, here's an SEM image of the microstructure of one of the cells, and you can see the thick LSGM electrolyte layer, the dense layer that's right here. Overall, the sum of these layers is quite thin, but you can see here there is, on the air electrode, we have our gas diffusion support, it's LSF. We have a nickel infiltrated LSGM fuel electrode that allows us to get high current densities for high triple phase boundary area, if you will. This is on an SLT support, which gives it strength, and one of the unique pieces of this is the nanoparticle nickel infiltration in the fuel electrode. If we look at the performance characteristics, we can get high performance. High performance here demonstrates at a power density of 1.6 watts per square centimeter at 650 C. As far as we know, that's one of the records. It works in both modes very well. The area-specific resistance is 0.18. We've been targeting 0.2 ohms square centimeter for the system, and we've demonstrated that at really button cell level. We have to do better on the 600C polarization curve, if you will, that's getting slightly higher, and we still need better performance there. But most interestingly, I think one of the tests that we've been running is on cycle durability. We need to cycle these things forward and backward, and no one has really tested this kind of technology in this mode. So we've looked here at really 1 and 12-hour cycles. You can see a 30-minute operation on one mode, 30-minute operation on the other, switching back and forth between these modes for different cycle times. So here is a 1-hour show, but we've also done 12-hour cycles as well. So 6 hours in one mode, 6 hours in the other mode at different operating current densities. And what you'll notice here is on this light blue curve, if you're just operating electrolysis mode, you get fairly rapid degradation. But as we change into cyclic mode, we get reduced degradation as exhibited by the change in total resistance over time. And we've tested this for 1,000 hours. And as you can see, once you get below a certain threshold operating current density, the degradation mechanisms are turned off, essentially, or interrupted. And we find that that actually happens around 0.8 amps per square centimeter, which is at least twice as high, or about twice as high as we think is economically needed to develop the technology. So we're really encouraged by these results in particular. In the remaining minutes, I'd like to give you a little snapshot of the economics. When we first presented a couple years back, there were a lot of questions on that. We had no data. I can report some data on this at this time. And that's unfortunate. Okay, I'm in IBM PC, and these equations aren't showing up. But what I would say is, briefly, there's a simple calculation that basically takes it takes the investment cost and divides by the energy storage and the round-trip efficiency and the number of cycles. And you get essentially a simple storage cost metric in cents per kilowatt hour. The challenge with this method is it assumes a 100% capacity factor in doing so. In order to they'll perform this, we need to cost out the plant. So we've done some bottom-up plant costing using some of these parameter values here, briefly highlighted here. 250 megawatt rating. We've shown we can get higher round trip efficiency, but we just put in 70% here. Mature life projections for solid oxide cell technology. Again, we're using costs from solid oxide fuel cells. They're very applicable here, but perhaps not exactly applicable depending on the cell material sets. The storage, there's a fair amount of good data here. We've been leveraging existing natural gas reservoir data from Lilletorp facility in Denmark, 120 million cubic meter natural gas reservoir facility. We make use of 70 million cubic meters of that. We need a 50 million cubic meter cushion gas to support the activity. And we've priced out that cost based on the existing cost that we know for that. And we've extrapolated for CO2 caverns. There, that's relatively unproven storage CO2. We've essentially taken the CH4 costs and more or less doubled them for the risk. In the end, we get a capital cost at this scale of around less than $1,100 per kilowatt. If you look at the total expense breakdown up here, it's not just capital costs. We got operating and maintenance costs here and staff and so forth to operate. But in the end, we're about 30% on the stack and less than 15% in the storage. This simple costing method then allows us to get us around 3 cents per kilowatt hour on storage costs with this method, which if you look, compares favorably against compressed air, hydrogen, and pumped hydro in these other bulk storage categories. We think that's perhaps a little too simple, and we could leverage instead the resources of this storage facility using electricity spot market prices and essentially using supply and demand characteristics of the grid market and do essentially market arbitrage to buy and sell power, essentially buy power cheap, charge your system, and sell it when the price of electricity is high. So the cautionary note here is in making these calculations, of course, we knew what the prices were. It's historic prices. And we could optimize the sell-buy strategy, which then means this is really a maximum annual income estimate. Okay? So if we look at 2008 electricity spot market prices, our colleagues in DTU really performed this study. They used the Danish market because that's what they were interested in at the time with our system. And we don't get a capacity factor of 100% in this scenario. We get 61%. And when you look at the life cycle cost, that raises it from almost 3 cents to almost 8 cents. But you do get revenue from this, and you can drop that by 4% to a net overall storage cost of just under 4 cents at 3.7 cents per kilowatt hour. There is lots of considerations that in the future, increasing renewable energy penetration will mean higher electricity price volatility, and you could essentially do more arbitrage under those scenarios. With those scenarios, then, there has been, because Denmark in particular is interested in 100% renewables integration by 2035. They are very seriously looking at then the price impact on their markets, and they have done scenario forecasting. We've used those forecasts with the 2008 buy-sell hour strategy, and we show that under that, and shown here in the red curve, is the buy-sell strategy and the spot market prices that might be expected in the future with high penetration. You could actually make money with electricity storage. Again, this is maximum, and of course there's lots of uncertainties here. But it does suggest that even if you weren't perfect, you might end up as zero cost on storage. Okay, so to wrap up here, we see that there are a lot of markets that we could enter within this technology. Not only this so-called power gas platform, we can do bulk storage, and more recently within the project confines, we're turning now our attention to distributed scale storage that will compete with advanced flow batteries and sodium sulfur batteries in the kilowatt hour to low megawatt hour ranges. There's a lot of work that certainly needs to be done yet. We really need to push the envelope on the operating temperature further with the LSGM technology. The results shown here are for small-scale cells. Okay? Cell scale-up is always a challenge, and that needs to be done. Long-term stability and durability testing, we have to operate in cyclic modes with the actual reactant gases we envision. And of course, if you're going to run this thing up and down, you need to know something about the dynamics of the capability of the system. So with that, I'd say we've learned a fair amount. We believe we can get fairly high round-trip efficiencies. We can even get above 80% if you can integrate thermally with nuclear or CSP, for example. And regardless of how we estimate the economics, we think that they're very attractive and can meet or exceed the DOE targets. With that, I'd like to thank some of my collaborators and open it up for questions.
Questions for Rob? You can do the back first, so yeah, that's easier.
Yeah, I have a question about if you guys have any problems with
Okay.
selectivity when you're running in electrolysis mode, converting the CO2 to methane. Do you have any issues with making C2s or products that you don't want?
No, actually, the electrodes are catalytically active enough that they reach equilibrium rapidly without even pulling out oxygen. When we pull out oxygen, obviously, we'll drive the equilibrium forward. But we make methane and CO and H2 as exactly as you might predict thermodynamically.
Nice work, Rob. Can you hear me?
Yeah.
Nice work. Can you care about a comment about the coking problem and whether you see it more in the electrolysis mode than in the fuel cell mode?
That's a good question because as you move from electrolysis mode, you're moving towards the coking boundary. Certainly one of the questions we have is, the thermodynamics analysis, is nice and it provides, insight and guidance on how to select conditions. But you really are dealing with local phenomena when you're flowing these reactant gases through the passages of the cell. And if you don't have a good distribution, you could have locally rich zones, so to speak, which could produce carbon deposition, which would degrade performance. So what's not so well known is what we would call the safety margin that would be required to push you away from that thermodynamic boundary. So what hydrogen and carbon ratio and what operating conditions would give you sufficient safety margin to not coke up. So that will be revealed more in the cell testing. As a part of this project, we built a pressurized rig at Northwestern, and they're going to be operating under syngas conditions at pressure and temperature, and that'll give us some better insight. Nevertheless, they're still fairly well-mixed conditions under the lab environment.
So how important it is to lower the operating temperature of these devices, and what do you think is the main barrier in that direction of research, or how you think you can achieve that goal?
Okay, so lowering the operating temperature really makes more sense. So at the large bulk scale, we don't think we need that lower temperature at this point. But when we start turning towards distributed scale systems, tens of kilowatts to hundreds of kilowatts or a megawatt, we think we basically, in order to keep the costs low, we want to strip out a lot of that BOP equipment that we can. So we think we can get relatively simple and elegant designs. However, we'd like to avoid pressurization in those situations as well. And so shown here, for example, is a round-trip efficiency versus stack temperature. We do have an expander included, but you can see that as we lower the stack temperature, we can get close to 78% round-trip efficiency at 600 C for one of these small-scale systems. And we really think we need, depending on whether or not you have the expander, you're going to be closer to 70% efficiency if you don't, but you really need the 600 C. The barriers are really the polarization resistances that are incurred. The resistances go up as you reduce temperature because the ionic conductivity of the cell goes down. One of the strategies could be to reduce the air electrode polarization resistance. We think there might be able to do that by doing more nanoparticle infiltration on that electrode, just like has been doing on the fuel electrode with nickel, except it might be done with Samaria, for example.
One last question.
Quick question. You mentioned in your cost analysis that your stack probably should last for at least 5 years. So could you explore a little bit and say why you believe it will be as long as 5 years?
Yeah, we don't know how long it will be. Right now, what we see is after 1,000 hours in these small-scale cell tests, virtually no degradation. The challenge is, of course, we have to operate on the carbonaceous fuel feedstocks we envision, and that hasn't been done over hours. The cycling doesn't seem at this point, okay, it seems like it does have promise. Other solid oxide cell technology has been demonstrated well past 20,000 hours. All the developers of that traditional focus in technology development are focused on increasing endurance. It's going to take certainly several years, I'm sure, to achieve that. But that's economically what the target has been. Some cells, like old Siemens tubular cells, they lasted 70,000 hours. But we think 40,000 is where you're going to have to start to enter the marketplace. That's real consistent with fuel cell technology.
Okay, let's take